So, Sharath, we can start our session. And today he is going to discuss about how we can use the remote sensing to detect the pollution in the land. Okay, over to you, Sharath.
Thank you. Yes, as Sir mentioned, today's topic is land pollution monitoring. Today's topic is land degradation is directly affects the agriculture, water system, food security, and even sustainable development. So we'll explore how modern satellite data and GIS and other analytical tools helps us to detect, analyze, and manage the land degradation and soil degradation at local and global level. So yeah, um, uh, like due to lot of rapid urbanization, climate change, industrial development, it leads to soil erosion and the loss of nutrients, salinity, desertification, soil cover loss, or even in the reduction in the whole productivity. So, remote sensing gives us the ability to monitor these issues continuously, repeatedly, and objectively over a large area. So, instead of depending on only on field survey, um, satellite data helps us to visualize how landscapes are changing in both the short and long term. So by the end of the session, I want all of you guys to be, understanding how remote sensing is used to assess the soil data, how multi temporal satellite data allows us to uh, detect the changes over seasons and years, and how measurable soil characters can be derived using spectral signatures. So these insights supports us to, for the decision maker for land restoration, agriculture planning, and natural resource management, etc. So remote sensing works in three different scales: satellite, aerial, and ground. So satellite platforms like Landsat, Sentinel, IRS, and Spot gives us large area coverage and a historical time series, which is essential to studying land degradation trends. Whereas we have aerial platforms that includes drones and aircrafts, which are efficient for fine details and perfect for mapping gullies, erosion patches, field scale soil variability, etc. Ground instrumentations like radiometer, spectrometers provides point level precision and act as a calibration reference for satellite data. So all these combined gives us the complete, comprehensive, holistic picture of the land and soil properties from local to national scales. So different soil properties reflect the lights differently in different portions of electromagnetic spectrum, right? So visible lights relates to soil color and mineral presence. Near infrared and shortwave infrared are excellent for detecting the moisture, organic matter, and soil minerals. Thermal infrared tells us about the temperature differences and thermal properties. Microwave sensors, especially radar, can penetrate the clouds, and it is very highly valuable for soil moisture detection as well. So, understanding these relationships gives us, an idea to choose the right data for right analysis. Okay, so soil reflectance depends upon three different categories of factors. That is uh, s- physical, chemical, and even moisture is very important because wet soil reflects far less light than dry soil. So when we analyze satellite reflectance, we are essentially interpreting these physical, chemical, and moisture characteristics indirectly. So, remote sensing in soil characteristics. Remote sensing helps us to translate these spectral signatures or spectral information into actual soil properties, field samples, lab spectral measurements from laboratory, and satellite observations works together actually. So machine learning techniques, regression models, band ratios, and spectral indices helps us to convert these spectral values into informations like organic matters that is present in the soil, soil fertility, moisture content of the soil, degradation status of the land. So all these makes the remote sensing an efficient tool for large area soil cover mapping. So monitoring degradation over time. Land degradation rarely happens in a single day. It's actually a gradual process. So multi-temporal imagery allows us to monitor the same area repeatedly over the months and years to understand the long-term trends. Vegetation indices like NDVI helps us to decline in the plant health, biomass, and overall productivity. So combining these data with land cover maps reveals where the ecosystem are losing resilience due to overgrazing, uh, and human pressures. Mapping soil salinity and waterlogging, it's also an important aspect. These are the major threats to productive of the land, especially in the irrigated agriculture region. So multispectral sensors helps us to identify the areas with high surface salt and stressed crops. Hyperspectral data can detect the subtle mineral absorption features, helping differentiate salt affected soils from waterlogged soils. So these maps helps the planner and decision maker where the drainage has to be there and reclamation or even soil treatment is necessary. High resolution imageries has transformed soil monitoring actually. So the gullies and drills are invisible in medium resolution data that can be mapped easily from the fine resolution satellite scenes or drone images. Stereo imagery even allows 3D analysis, helping the researchers to estimate the gully depth and erosion volumes. So this actually helps us to prioritize the treatment area and design the erosion control strategies. Land degradation and hotspot identification. GIS allows us to combine the satellite data with terrain maps, land use data, and socioeconomic indicators. The result is powerful system that can highlight the where uh, uh, degradation is happening actually and why it is happening, which area need the prioritized action. So these hotspot maps are extremely useful for government programs and international monitoring initiatives. So this slides summarize the general workflow of land degradation mapping methodology, data collection from multiple sensors, pre-processing and atmospheric correction, calculation of spectral indices, integration it with GIS layers, classifying and change detection, field validation, and finally reporting and dissemination. So this is the schematic approach enables the reliable scientific outputs. So prediction of future land degradation status. So with the help of machine learning and spatial modeling, we can go beyond mapping that present. We can simulate the future as well. Using historical patterns, soil condition, climate, and human activity data, models can forecast where the degradation risks are highest. So this helps the policymaker and plan interventions proactively, not reactively. So here we see the real world example derived from the multi-season list 3 data. By comparing the reflectance from different periods, we identify where the salinity spreads over time. Multi-season data is crucial because salinity often appear seasonally depending on the irrigation and the evaporation cycle. Now, soil moisture estimation. It is one of the strongest application of polarimetric SAR data, that is synthetic radar aperture. So radar penetrates clouds, as we already seen, and can sense the moisture even at night. It is light independent, and a different polarization combines helps the separate the moisture from the vegetation and soil roughness. This is extremely useful for drought assessment, irrigation management, and crop monitoring. Land use planning and conservation. For planners, remote sensing helps to balance the development with the environmental safety, whether it is agriculture, forest management, or for watershed development, or urban planning. For all these, satellite data provides the measurable evidence of land status. So this ensure the resource development is sustained and data driven. So GIS act as the central platform where remote sensing data, terrain data, soil data, climate data, and even socioeconomic data comes together. So it allows the powerful spatial analysis, visualization, and simulations for future projection as well. GIS-based decision support system are widely used for rehabilitation, uh, watershed planning, policy formulation, and project management and monitoring. So, although powerful soil remote sensing has, but it also has its own challenges. Vegetation cover often hides the soil, and different soil have uh, a similar spectral signature as well. And atmospheric effect actually reduce the data clarity, and noise in the satellite data can weaken the spectral signals. So addressing these are very much needed for the pre-processing, good field calibration, and advancement in the analytical technique. So this is the schematic reinforce the complete workflow from the image, the acquisition to final maps. This highlights how field measurements, spectral analysis, and GIS integration are essential component of the reliable soil information system. Um, so this slides indicates the remote soil mapping faces some of the practical limitations as well. We have mixed pixel, which has soil plus vegetation plus residue as well. So coarse resolution missing micro features and insufficient field samples reducing the model confidence as well. So the reliability of the model is directly proportional to the field samples. So solutions includes high resolution imagery and ground truthing and improving the classification methods. So recent innovation have dramatically improved the soil studies. Stereotypical satellite helps us in 3D terrain mapping, and hyperspectral sensors detect very subtle chemical and mineral variations. Ground penetration radar like SAR helps us to map the subsurface layers and underwater aquifers. So this slide shows the how soil informatics is important, and what is the role of digital soil banks. Digital soil database store the large collection of data in soil information, field data, remote sensing data, laboratory data, spectral signature maps, and etc. So they ensure the long-term accessibility and consistency. Integrated with GIS and dashboards, they helps the researchers and planners and farmers even better decision and strategy planning. So this image is an example of the village level soil map showing different soil units within the rural landscape. Such detailed map greatly helps the farmers and administrators to understand the local soil constraints and plan the management interventions. So this map shows which area are suitable for different types of crops based on the soil texture, moisture, fertility, and slope. So thus, suitability analysis prevents wasteful crop selection and leads to the higher agriculture productivity. So here we evaluate the land in terms of what it is capable of supporting, how well it is being irrigated, and by understanding the capabilities constraint, map land managers can avoid the unsuitable use and long-term degradation. Future prospects. So the future of soil remote sensing is moving towards the micro level management, very high resolution satellite, hyperspectral radar, hyperspectral imaging, radar imageries, real-time monitoring dashboards, automated alerts. So this brings us closer to precision agriculture and targeted interventions. So remote sensing supports uh, precision agriculture, irrigation optimization, crop selection planning, etc. So the farmers can apply the fertilizer, irrigation, or treatment only where it is needed, saving the cost and improved yield. Land degradation and land degradation policy and decision making. Data driven governance is very essential for this step, and satellite based monitoring helps us to track the degradation regularly and measure the impact of the conservation effects and support the transparent reporting. Practical application. Some of the common real world application includes mapping the salt affected area, tracking gully erosion, identifying the land capability, and monitoring the reclamation progress. So these helps the governments and local agencies to take the timely corrective actions. So to summarize the key methodology for the soil reflectance analysis. So it helps us to assess the soil and vegetative properties. Vegetative indices like NDVI, SAVI act as indirect indicators for soil and ecosystem health. GIS and spatial modeling integrates these data to produce the actionable insights. Together, these methods forms the backbone of the modern land monitoring. So RS in sustainable development, it supports the sustainable development goals linked domain like land conservation, climate adaptation, deforestation tracking, and water resource management. So despite major progress, we have some gaps as well, disadvantages. So we need for the better ground validation and need for the fine spatial resolution for more sensors, and we need to improve the vegetation masking techniques. So continuous research and technical development will bridge these gaps, I guess. So this particular slide reinforces the idea that land degradation is very dynamic and regular monitoring is very critical. Without consistent observation, soil deterioration can reach the irreversible state and before we notice. Emerging technologies, uh, machine learning and big data analytics are reshaping the soil classification and degradation forecasting. So these techniques automatically recognize the spectral patterns and derive the prediction faster and with greater consistency supporting the smarter land management. So policy recommendation for effective implementation, regular monitoring cycle, strong institutional training or and expansion of RSGIS capacity. So all these ensure the techniques is not just available but actually being effectively used. So to summarize, um, remote sensing and GIS have developed into indecisible tools for soil and land resource management. So they enable the objective and repeatable monitoring, large scale assessment, data driven planning. So as the sensor resolution improves and the computational tool advances, we are moving into the future where every field can be managed and managed with precision and sustainability using the spatial data. So uh, I've done with the presentation. So before getting into the practical session, let me just show you a case study. Uh, this is one of the master's research work. So this research is mainly to monitor and predict the impact of climate change induced flooding and inundation on the urbanization pattern using remote sensing and machine learning techniques. So with a special focus of Greater Kochi Corporation Authority region, Kochi, Kerala. So let me just quickly run through the slides of this. So methodology is very important. So from the Hydrojet DEM and Sentinel-2, I have taken the flood inundation mapping, and LULC and LST maps have taken from Sentinel-2 and Landsat 8 and 7. Climate data have been pre-processed, and it has been projected to the for the precipitation and mean temperature level. STAR data and uh, European Space Agency's climate change initiative. I have retrieved the human settlement layer and topographical wetness index. So altogether, I have reviewed the major flooding event of Kerala happened in 2018, and I have discussed the city growth consequences on climate change of the landscape of the Kochi region. This is the base map and elevation, slope. So both of these are used, yes, using. So these map are generated using SRTM data, 30-meter resolution. For elevation map, the units are in meters, and for slope in percentage. So I have retrieved the road network for this region using Survey of India topo sheet and ESRA. And through that road network, I have done the density analysis and distance from road, that is proximity. Same goes for railway tracks. So here is the topographical wetness index, which is unitless, and I have normalized difference moisture index (NDMI). This is also unitless, and I've done land surface temperature for the year 2000, 2010, and 2024. So 2000 is done by using Landsat 7 ETM plus. 2010 is also the same data. And for 2024, I've used Sentinel-2 multispectral imager. And this is the land LST change from 2000 to 2010. And this is the LST change from 2010 to 24. And the LST value is in degrees Celsius. And it is the time series analysis from 2014 to present. This is the daytime LST over urban areas and water body, and nighttime LST over urban areas and water body. And here comes LULC changes from 2000 to 2010 to 2024. Finally, it has been projected to 2030 using machine learning techniques. This is the aerial coverage of different LULC classes over the study area. And this is the statistical analysis and overall accuracy assessment and kappa coefficient. This is for 2010, this is for 2024. And this is the projected LULC for 2030. And you can see the gradual increase in the built up area and dramatic decrease in the dense vegetation. So this is the model I've run using Google Earth Engine for overall training and validation accuracy. And you can see the urban sprawl, how the built-up area is increasing and other non-urban area is gradually decreasing. And using the climate change initiative from European Space Agency, I have mapped the settlement area from 1995 to 2025. Also, it has been projected to 2030. So here is the small animation that shows how the urban sprawl is happening over the years. Uh, it is 1995 to 2025, and it is the flood vulnerability assessment, flood vulnerability map after the assessment, where we can see it is highly vulnerable uh, around the water body, that is Vemanad Lake. Uh, Usually, during high tide time, the Kochi city is highly prone for flood. So this is the climatological model where I have projected the annual uh, average mean surface air temperature, and this is for precipitation. So yeah, on the whole, the study has found that the region of Maradu, Kalamassery, and Tripunithura are highly affected, and residential part in Maradu and IT parks in Kalamassery, heritage tourism and residential buildings in Tripunithura are accelerating the urban growth. So all these are influencing the flooding event annually in the Kochi region. One minute. Excuse. Sorry. I'm back. Okay. Let's just um get into the practical session. Can anybody confirm whether I'm presenting and I'm audible?
Yes, Sharath, you're audible.
Thank you. Okay. So in today's session, we'll be practical session. We'll be seeing how the DEM can be, visualized, DEM data, and also LULC from dynamic world data, and NDVI and other spectral indices. Also, we'll be seeing how the time series analysis of NDVI and LST can be done. Finally, vegetation health index for or steady area is also been going to visualized. So the steady area is around Kochi region, Ernakulam, Kerala. Only for the VHI, Coimbatore has been selected. Coimbatore city, Tamil Nadu has been selected because it is a good combination of both urban growth and forest degradation. So Yeah, that's the reason for Coimbatore city for that particular study. Let's just run the code. So this is for uh, digital elevation model and its related products. Let's just look at the result first, and I will explain the code block by block. So this is the region of interest, and this is the DEM 30-meter resolution. Slope, I think some error happened on slope. Slope is not visualizing properly in the code. And this is the aspect. Aspect is nothing but the direction of slope. And this is the allows dim data. So here is a histogram of the elevation. First one is for the uh, uh, average. Sorry, first one is for the elevation, and second one is for the average. Okay. So in this code, firstly we have loaded the SRTM data, which is 30-meter resolution, and we're also loading the allows dim. And then this is just for the day three visualization, this topic. So just leave. And then mm, here, uh, excuse me, I'm getting a call. Okay. So yes, now this is to visualize the DEM data, which is from SRTM. So white, green, and black is the color palette that we are going to use. And we are naming the layer as DEM 30. And we are clipping it for the ROI. So here, the ROI, the region of interest that we have specified is quite different. I've just pointed the coordinate lat long in the map, and I have created the buffer for 20 kilometers. So that's why we are showing that round circle type steady area over the map. So yeah, we are just clipping the SRTM 30-meter resolution DEM using the ROI region that we have assigned as here. Sorry, here. Okay. So again, the allows DEM is also being visualized with the same color palette and visualization properties. So yes, and that's how we can able to visualize all these DEM products in the map. So second code is LOLC, recent LOLC using World Dynamics data for Ernakulam, Kerala. Yes. So this is the visualization. So we haven't done anything. That just we have coded the the data uh, which has already been established in the website. We are just importing it from it, and then we are clipping it over our particular study area. That's it. So this LOLC data has been classified into different classes. That is water, tree, grass, flooded vegetation, crops, shrubs and grubs, and uh, built up area, bare ground, snow and ice. So snow and ice, it's not possible in the Kochi region, but still it is showing because the LOLC has been classified into these many classes. Okay, let's just look upon the codes now. Same story, ROI has been coded, and then the data is from FAO. Also, We are importing the data from Google Dynamic World V1 data. So the year that we are filtering out is 2024 and 25 for the month from January to December. So this data is for the latest map, that is 2024. We are using the color palette. So instead of these codes, we can also give the words like red, blue, light blue, green, etc. So, and this particular block of code is just for adding the legend into the map. And that's it. If you want to export the map into your Google Drive, this is the code. Just remove all these double slashes and just click run. We'll be getting the map ready to export. Ready to export in the task bar. See, the map 2024, it has been named as annual map and it is ready to store in our Google Drive. So this is the study area. This is the NDVI map of 2025. NDVI is nothing but uh, normalized difference vegetative index. And this is the chlorophyll index. And this is EVI for 2025. EVI is nothing but enhanced vegetative index. Okay. And this is RECI, that is red edge chlorophyll index. We can also see the time series analysis of all these parameters. So this is for NDVI 2070 to 25. This is chlorophyll index. This is enhanced vegetative index. This is red edge chlorophyll index. Right. This is the study area. This is uh, the map NBR. NBR is nothing but normalized burnt ratio. This uh, uh, layer is very, very important for forest fire mapping or the urban heat island. This is SAVI, that is soil adjusted vegetative index. We have used the same color palette for all the layers for some reason because it gives the uh, comparative analysis, comparative assessment when it's exported and imported in different software. So this is EVI, or we have already seen about this layer, enhanced vegetative index. Let's just look at the code now. Simple. It's like each block of code has been already explained, but still here we have cloud filtering technique as well, and we are importing the Sentinel to harmonized data, which is under the 20 percent cover, cloud cover from the year Jan 1st of 2025 to October 31st of 2025. This is very recent land indices of the study area, and for NBR, normalized burnt ratio, the formula is band 8 minus band 12 divided by band 8 plus band 12. So uh, for the 30-meter scale, the ROI has been clipped and it has been visualized. The same story. I'll just say the formula for SAVI, that is near infrared minus red divided by near infrared plus red plus L into 1 plus L, but the L is just a constant which is 0.5, and the band has scaled by to 0 to 1 by dividing by 10,000. That's it. That is the science behind it. And then for EVI, uh, it is 2.5 into near infrared minus red divided by near infrared plus 6 into red minus 7.5 into blue plus 1. So blue, red, all these are the bands that has been retrieved from Sentinel-2. All the band is called with that names. That's it. So yeah, and then yeah, directly visualizing it. And if you want to export the maps into your G Drive, the same code will be followed for here also. And here comes the time series analysis of NDVI and LST. Let's just run the code. Not just time series analysis, we are visualizing the TCC, that is true color composite, and false color composite of the Sentinel-2 data for the study area. This is the string area. And this is the true color composite. It's nothing but the true imagery. That is the real world imagery from the satellite. And this is false color composite. It enhances the forestry and vegetation as bright red color, and water as bright blue color. And this is the LST pre-monsoon of 2024. Okay. This is the LST land surface temperature for the post-monsoon 2024. All these blue colors are nothing but clouds. This is normalized difference vegetative index pre-monsoon 2024, and this is post-monsoon 2024. Let's just decode the code. So yeah. So first, it's for creating the uh, steady area, the same coordinate and same buffering distance. And we are, for time series analysis, we are filtering out the start date from 2005, January 1st, and end date as 2025, 12/31st, up to the data availability. So Landsat 8 has been imported, and we are extracting the band 4, band 3, band 2 for true color, and band 5 for near infrared for vegetation, and band 10 for thermal band for LST. So we are uh, defining the function to STB10 from Kelvin to Celsius here, and then we are adding the LST Celsius to each image. And then we are defining the function to compute the NDVI, that is near infrared minus red divided by near infrared plus red. And the same visualizing parameter that we have used TCC is being followed for FCC as well. And seasonal analysis, pre-monsoon is considered for the months March to May, and post-monsoon October to December. So these same month classification is followed for both the layers LST and NDVI. Yes, and that's it. Let's just look at the. So yes, so we can see the deep decline for the uh, year before 2018 because of the cloud cover, not just because of the 2018 major flooding event in Kerala, but it is due to the cloud cover before 2028. Okay. This is the last code, vegetative health index. We are deriving vegetative health index through vegetation condition index and temperature condition index. So for this study, the area is Coimbatore city, in and around Coimbatore city, Tamil Nadu. It actually takes more time because to compute the all the pixel values, it's hard because the digital numbers and reflectant values involves so many computations over this map. Rather than look at this map, let's just focus on the uh, time series analysis. So this red color line bar indicating the vegetation condition index, and uh, blue indicates the temperature condition index, and this orangish yellow color indicates the vegetation health index. This is the uh, time series analysis, and all these are just individual computation of these bars. So yeah, as usual, we are defining the area, but now the coordinate has been different, and we are uh, creating the buffer for 30 kilometer, not 20 kilometer, and we are filtering out the date 2001 to 2024, and we are importing the data from MODIS NDVI and MODIS LST 1 kilometer data resolution, and we are assigning the maximum minimum value for NDVI, and we are importing the data and clipping it over and filtering out to our date range. And this is the monthly NDVI visualization. And there are some formulas. So after computation of the NDVI, we are computing the VCI, that is with the formula NDVI minus NDVI minimum divided by NDVI maximum minus NDVI minimum. For TCI, that is temperature condition index, LST max minus LST divided by LST max minus LST minimum. So after that, VHI, that is vegetative health index, is equal to 0.5 into VCI plus 0.5 into TCI. So that's a simple formula to compute the VHI and establishing it in the time series analysis. Yes, and that's it. Any doubts? Any clarification? The session is open for discussion or any clarification, doubts, or any opinion that you can share about the presentation of all 3 days. Any suggestions you can give to the presentation. Okay, in Google Earth Engine, you showed some charts. Can you just show how to open the chart? Okay, so here is the chart. You see the open tab symbol over here. Just click. You'll open a new tab with the zoomed image. You can download this as CSV, or you can download this as SVG or PNG. Just click over this icon. You will get the new tab. Yes. Oops, sorry. Sorry. Yes. See, can you see this new tab symbol over here? You can see this new tab icon for all the charts that has been generated in the console tab. So you can just click over here and you will able to see the new tab with the zoomed image. So you can have see the download options over here. That's it. Okay, suggest me any specific course to learn remote sensing. There are n number of uh, availability of RS and GIS tutorials in YouTube and other platforms. You can have Udemy courses. You can take up Coursera courses. There are so many opportunities in websites. I would suggest you to start from the basic. Start reading the reprints and research papers related to uh, RS and GIS. Nowadays, there are so many papers are getting published using many high-end technologies like machine learning techniques, artificial intelligence, etc. But to start with, take the paper, choose the paper wisely, where people have used simple methodology, retrieving the data and retrieving the environmental properties from simple methodologies and research workflow. Start with that, you will easily cope up with the current trends, I guess. Anything else? Um, so for a different study area, we need to enter different coordinates, right? So can you show how to enter the coordinates and how we get the coordinates from Google Map? Okay. So these coordinates can be taken from Google itself. Um, you can see, let me share the screen again. You can just ask the Google, like, this is the coordinate for Coimbatore city, and just paste it. Just ask the Google, like, I'm using Microsoft Edge software. You can use, sorry, browser. You can use any browser like this. Give me coordinates for any city. Like, for example, Madurai. Madurai. Tamil Nadu. It is. Yes. See, we got the lat long values. Just copy paste it over here. Copy and run it. It'll take time. So that's how you will take the coordinates. Anything else? It ran successfully. Like, see, the coordinates that I've given has been run, and it came up with the time series analysis as well. Okay, Google. So you, what you want to learn, like, so Google Earth Engine is uh, basically works on JavaScript. If you want to learn codings, I would suggest you to learn Python, as I said before in the yesterday's session, because Python is the fourth running language comparing it with others. But for Google Earth Engine, all the codes, it's been scripted already in the catalog of Google Earth Engine repository. You can take and use it directly from that. Or there are a number of codes that has been designed and scripted are readily available in the websites. You can take, copy paste it, and just run according to your objective of the study and study area. That's it. But if you're really interested in taking up the learning of computer programming, I would suggest you to learn Python, or any because I'm suggesting Python because it's very easy to understand. It is very simple as we speak. So yeah, anything else?
Sharath, I think there are no more questions from the student side. So can we wind up our today's session?
Sure, sure.
Yeah, I
Before
think,
winding up, I would like to
yeah.
thank you and for the Ecor Foundation for giving me this opportunity, because it's a good journey for the small learning for me as well, and I'm very happy to share my knowledge, what I have learned, to all you guys. Thank you.
Okay, thank you so much. And I would like to express my sincere gratitude to Mr. Sharath Kumar Re, as well as the participants who joined with us in the last 3 days to learn about the remote sensing and how it can be applicable in different aspect of pollutions like air pollutions, water pollutions, and the water pollution, air pollution, and land pollution. So today is the last day, as you know, and we will wind up our today's sessions. And I believe that this session was insightful for each and every one of you. And we will give you a certificate in 2 week of time. And the recorded sessions will be available in our YouTube channel, as I will mail you those links to you by 2 week of time as well. Okay, thank you so much. Maybe we will meet again in a different session that is related to remote sensing or something else. And we have two more sessions tomorrow and after tomorrow that is quite different and is related to the marine and marine aspects. Two of them. One is by one research scholar from National Taiwan University, and one is by one scientist from India. And both of those people will be discussing about their research and new niches in the marine science. And that is quite open for everyone, so you can attend it for freely unless you need a certificate. But for the certificate, you need to pay. Okay, thank you so much. Thank you. If you need the more details, then I can possibly share it with you now. The two sessions, the tomorrow sessions, registration link, and everything is in the chat box. You can see, and if you find it is interesting, then you can participate, or we appreciate if you could share it with your friends. Yeah. Okay. Yeah, this is, I think this is exceeding the size. It's fine. Yeah, this one. Maybe you can register or you can share it with your friends. Okay, thank you so much.